showed 18 years ago, I guess. There are very general, there's a general theorem about secret sharing schemes, which tells us that anything that isn't obviously impossible is possible in the way of secret sharing. So in particular, if we want to share our state psi split up into states psi ij, and it's going to be simplest if I write psi ij to mean the same thing as psi ji here, where I and j are different. I could do it in a way so that the psi can be reconstructed from any set that contains all of the things corresponding to one of the labels. So here, this set I has all the psi ij's for every j that's not equal to I. The point being that no two of those sets are disjoint, because Si and Sj always contain psi ij, so you don't violate no cloning. And it turns out that as long as you're not violating no cloning in your design structure, there is a way of finding a secret sharing scheme. So given that, and this slide, no, let me stick with this for a minute then. Given that you're home, because if you think about what this means, it means that if you get a call at CI, well, it doesn't, for each pair of diamonds that includes I, so for each ij, the state psi ij will be returned to Ri. Doesn't matter whether your diamond is the preceding or the succeeding one, so to speak, in the causal relationship. Either way, it will get to the right return point. So all the psi ij's will get to Ri, and then you can reconstruct the state from the set of all the psi ij's and hand it over. So this just recaps what I said, but maybe it bears repeating. You can always make the secret sharing work as long as you have an access structure that's monotonic. I mean, obviously, if you've got some set of states, you can build the state from it, and you add more states to it, you can still build the state from it, and it doesn't violate no cloning. And that's true for the sort of secret sharing scheme we want, so it all works. So I was puzzled, and my collaborator Emily and I were both puzzled for quite a while, not by the algorithm, which is beautiful, and the theorem, which is lovely, but by Patrick and Alex's interpretation of what it's telling us. I think after talking with Patrick, I think I understand much better. So here are the things they say in their abstract. We fully characterize which regions of space-time can all hold the same quantum information. Replication of the information in any configuration of space-time regions not leading to violations of causality or the no-cloning theorem is allowed. This provides a simple and complete description of where and when a qubit can be located in space-time, or in a general state can be located in space-time, revealing a remarkable variety of possibilities. So, well, I'm still not sure about the completely general part, because we're still talking about a task with a finite number of call and return points. And what puzzled me for quite a while was that what happens in this task depends on where the calls come in. And these statements don't seem to be saying anything about calls and returns. They just seem to be saying something abstract about the propagation of quantum information in space and time. But I think a little therapy with Patrick has got me through that. So, I mean, certainly as they say, there's what we already knew was that if you have an unknown state and space is going this way and time is going this way, no cloning tells you can't make a copy of it in space, but unitarity tells you if nothing else is going on and it's just propagating, there's a sense in which you make an uncountably infinite number of copies of it. It's sort of easier to see if h equals 0, I guess, but in time. States are replicating themselves in time all the time, so to speak. And somehow you want to see how those seem like the sort of singular special cases of some general statement that we should be trying to make about what happens to quantum information. Can it be here and here? And how? And in any concrete example, is it in some sense evolving through some set of regions of space-time, so that it's here, in here, and in here, and in here, and in here? And if so, what's the story there? What do we actually say in any physical situation? So I don't know that they completely allow us to answer that, but they do tell us what happens in this sort of task. And I think the key thing, the thing that was bugging me, is if you want to think abstractly what could be going on, don't worry about the calls. Think about a version of this task in which Alice is ready for a call to come in, but it never actually comes in. So, and maybe it's easiest, I'll go back to their example. So the right statement then is if no calls come in, but Alice follows the algorithm, there will be, in each of the causal diamonds, at least one space-like or light-like, in the singular case, surface that contains enough quantum information to reconstruct the state. So in this case, if no calls come in, a secret will go from here to here, and a secret will go from here to here, and, well, because this is a singular example, it's light-like, but there will be one share of the secret here, and one share of the secret here, and so enough information to reconstruct the state on this surface which is within the diamond. In fact, in this case, is the diamond. And similarly here and here. And that's true in any example for which satisfies the conditions of the theorem. If no calls come in, then there is a sense in which the state is replicated in each one of these causal diamonds, even though there is no causal path through the causal diamonds. That's about as much exegesis as I can offer of their comments. I'm sure Patrick and Alex would say more. And I don't quite know, it seems like a starting point for thinking about what's happened, what the real story, the full story about quantum information propagating in space-time is and its replication. To me, it doesn't seem like the end, but it's at least gives you something on which to build a more complete story. So there are lots of nuances and lots of variations of summoning that challenge one's intuition a little bit. And one of the reasons why Emily and I were so bugged by Patrick and Alex's comments is that we were thinking about one of these variations. So it's quite a natural question. Suppose we allow Bob to demand the state at several places, at several call points. He makes several summonses. We've already seen it's just not fair for him to expect the state to be returned at each point where he calls for it, because Alice can't clone it. But suppose we give her a more relaxed and apparently feasible task and say, well, you may get many calls, but if you do, you only have to return the state at one of the corresponding return points. So if you get 7 calls, it's up to you. You can return it at any one of the 7 return points. So that seems, on the face of it, as though it should be easier for Alice. At least it seemed to us as though, initially seemed to us as though it should be easier. Previously she was constrained to return at precisely 1 point. Now she has choice. It isn't. It turns out to make the task strictly harder, by which I mean it's possible only for a strict subset of the configurations for which the Hayden-May version of the task is possible. So you need the Hayden-May conditions, And you also need a complete causal ordering of the causal diamonds for this task to be satisfied. If people want to go through the proof, we could discuss it afterwards, but it's not very long, but I won't worry about it here. So for instance, this lovely little example is not possible if Alice knows there could be 1 or 2 or 3 calls, and if there are 2 or 3 calls, then she gets to choose where to return the thing. So that's a little bit of a challenge, at least for us, it was a little bit of a challenge to the intuition. Yeah.
Could you go back?
Yeah.
This condition is causal ordering. That does not imply the main conditions?
No. Causal ordering means that there's something like such that there's a causal path where, so di less than dj means path from I to j.
So they still doesn't have to be one of...
Oh, wait, sorry. Yeah, and it's transitive. So there has to be a causal path from D1 into D2 and into D3 and into D, all the other diamonds.
But there doesn't have to be one that goes from the first to the second to the third.
There still doesn't have to be a single path going through all of them. So it's not as... It's somewhere in between the Hayden-May conditions and the trivially satisfiable things. Yeah.
Can you give us a quick example of something that sits in the middle? If you can do that on your feet.
So wish I'd prepared one. Yeah, yes, I can. Can I do it? Can I do it right now? I'm not sure. Probably. Let's see. The sort of thing you want is that you can get from here to here, and you can get from here to... Yeah, I haven't drawn that right. No, still haven't drawn it right. Here to... Oh no, that's not... yeah, but you have to do it in 3D. So you can get from here to here, and you can get from here to here, and you can get from here to here. I think so, because of the transitivity. I mean, danger of saying something wrong on sort of while thinking on my feet, but.
Oh, I see. Okay, yeah. Okay, I've got a flavor for it now.
If you want an answer instantly, there's one in our paper, so you can, yeah, I can do it over coffee. So, there is something nicely paradoxical about that. There is a resolution, like all paradoxes. The more you think about it, the less paradoxical it becomes. And the resolution here is, one way of thinking about the resolution is that the knowledge that a single call will come in is actually in itself a sort of non-local resource that helps Alice. So, she knows when she gets a call at some point that there will be no call at any other point, and therefore she knows that there will be a possibility of organised cooperation between the points that relies on those correlations. If she loses that reliance on the correlations, she's got a coordination problem, and that turns out always never to make life easier for her, and sometimes to make life harder. So, you could generalize the idea of summoning in lots of ways. I'll just give you one more. So far I've talked about summoning as though it's literally that, call or return. But you could think of it as a slightly more abstract task in which classical information in the form of some integer in a known range is arriving at a set of points. And the collective, there's some joint function of all that classical information that determines a return point from, let's say, some finite list. So here, Alice is going to get an integer here, and another integer here, another integer here. And she knows in advance, given all these integers, how to compute the value of the return point. And I'm interested here in the case where the ranges of these things are known and there's no other constraint. So she can't rely on any correlation between M1 and M2 or any of the other M's. All possible, everything consistent with these ranges is a possible set of inputs. So for the many call, if 0 is included in many version of the task that I just described, is an example of a thing without constraints.